Hi friends, let us see a type 3 technique of designing an FIR filter using windowing method. Now let us take a problem. For example, this is a given problem. It states that design an FIR digital filter to approximate an ideal low pass filter with a passband gain of unity, cutoff frequency of 850 Hz and working at sampling frequency of 5000 Hz. The length of the impulse response should be 5. Use rectangular and Hamming window. So let us first jot down all the given aspects in the question. So the given data over here is, first of all, they have said that we need to design a low pass filter. So the given filter is a low pass filter, okay, with a passband gain of unity. So let me write the passband gain. We will write as G of P as 1. Cutoff frequency, it is given as FC, which is 850 Hz, and the sampling frequency is given as 5000 Hz. They said that the length of the impulse response should be 5. That means the capital N is given as 5, and and they have specified that use both the windows, but let us see using Hamming window alone. So you can use any one of them. You can use either Hamming or you can use a rectangular. So how to proceed in this problem? This problem is not as similar to that of type 2 or type 1. That's why I have segregated it as type 3. In this problem, we need to actually develop HD of e raised to j omega. Okay, so we have to come first to type 2 level, then we will go to type 1 level HD of e raised to j omega, and then we will proceed the problem. So as per the given data, first we need to bring our HD of e raised to j omega. To get HD of e raised to j omega, I need to first find why they have given me Fs or Fc and Fs, that is the sampling frequency. The reason for it is the given aspect, all the aspects that are given over here are in the analog domain. So this domain is analog domain. And they are asking me to find a digital filter, that is digital domain system. So first I need to translate my analog domain to digital domain, get the data of digital domain and design a system of digital domain from the analog. So let us first derive our digital domain characteristics. So your step 1 of the solution is digital domain characteristics. Okay, so I need to first find the digital domain characteristics. Okay, now first we need the cutoff frequency. The cutoff frequency here is given as Fc, which is equal to 850 Hz, which is an analog domain, and they have specified the sampling frequency, which is 5000 Hz. So we need to first get the digital cutoff frequency, which I write as capital Fs. So this is my digital frequency Fs, which is small fs upon small fc upon Fs, which is 850 upon 5000. Okay, so that comes around 0.17 cycles per second. Okay, now I don't want Fc, I want omega c. So to get omega c, I will just multiply Fc by capital Fc by 2 pi. So that is 2 pi into 0.17 will give me radians per sample, that comes as 1.068. Let's say this is my radians. Okay, so that this is my discrete frequency. Okay, they have said that the passband gain is of 1. Okay, so this was the first characteristic. Let us do the second characteristic. I want hd of e raised to j omega, right? So hd of e raised to j omega can be derived from the given characteristics as the passband gain is given as 1, right? Passband means what? Till cutoff frequency. So how to determine the cutoff frequency? So in the problem they have specified that the given problem is of a low pass filter. So how will my low pass filter look like? My low pass filter will be looking like from here to 1.068. Okay, this is my omega, this is my minus omega, so here it will be minus 1.068. So from 0 to 1.068 and 0 to minus 1.068 I will have the pass band, and then up to minus pi and here up to pi I will have 0. Agreed? And they say that the pass band gain is 1, so the height over here is 1. So I have written 1 over here. Agreed? Now we want e raised to j something over here, so that is not given. But this is the pass band, in the pass band only the hd of e raised to j omega is 1. Rest everywhere it is 0. So it is 0. So I need to put the restriction on 1. So I will put the restriction like this: 0 less than equal to mod omega less than equal to 1.068 radians. That means till the cutoff frequency 1.068 I will get 1 in negative and positive direction, and after that it is 0. So from 1.068 less than equal to mod omega less than equal to pi I will have 0. So this region it will be 0, this region it will be 0, and here it will be 1. Okay, so I have developed or built hd of e raised to j omega. This is type, we have reached type 2. Still we have not got till type 1. Okay, so to get till type 3, type 2 from type 3 I have added 2 more steps. One is building up the cutoff frequency and then developing the type 2 transfer function or hd of e raised to j omega. Third, we need to get type 1 problem, right? Now here we require e raised to minus j alpha omega. That will be, we have m given as 5 and alpha is equal to m minus 1 by 2. So I will get 5 minus 1 by 2, which is nothing but alpha will be equal to 5 minus 1 is 4 by 2, which is okay. So finally my hd of e raised to j omega looks like hd of e raised to j omega will be equal to, because passband gain is unity, it will be 1 e raised to minus j, alpha is 2 omega, and it will come as 0 less than equal to mod omega less than equal to 1.068. and is 0 from 1.068 less than equal to mod omega less than equal to pi. Okay, so that is what the given problem is. Now this, if we look at, it's a type 1 problem. So where we started from? We started from type 3 problem. We have written the analog characteristics of the filter. Then we went to digital characteristics, obtained the digital characteristics. We first obtained type 2 transfer function or HD of e raised to j omega in type 2 form, and then we came to type 1 form using the M. Now we have reached type 1. Now we will use our normal methodology. So now step 2 over here will be apply I DFT. So to apply I DFT, I will have to use the formula h of n 1 upon 2 pi integral from minus pi to pi h d of e raised to j omega n d omega. So that will be 1 upon 2 pi. Now from minus pi to pi, again let us see the regions from minus pi to pi. From minus pi to pi, the region minus 1.068 to 1.068 is where the passband is 1, rest everywhere it is 0. So here the integration will go to 0, and only in this middle region will get the response. So I will have the integral going from minus 1.068 to 1.068. Okay, in this hd of e raised to j omega is e raised to minus j 2 omega e raised to j omega n d omega. That will be 1 upon 2 pi. Okay, and if we solve this integral, you will get e raised to n minus 2 with a j over here, omega divided by j n minus 2 with minus 1.068 to 1.068. This will lead to 1 upon pi, because 2 will get absorbed with this j, n minus 2 into sine, okay, n minus 2 into 1.068. Okay, so this is my final h of n, which is again infinite. So what I need to do? I need to convert this infinite samples to finite samples. So step number 3. So step 3 says that we need to obtain finite h of n, which is h dash of n, which will be given by h of n multiplied by w of n. Now I have two h of n given to me, sorry, w of n given to me. One is the rectangular window and one is the Hamming window. So let us form a structure. Like I'll start with my n, then I will write my h of n, which is nothing but 1 upon pi n minus 2 into sine n minus 2 into 1.068. This is whole thing is in the angle. Then we have w, let's say Hamming of n, and we will have rectangular window as WR of n, and then finally we will get h dash of n. Now I will write h dash of n with respect to Hamming and h dash of n with respect to the rectangular window. So both we will write. Okay. So this is my function is n will take value as 0, 1, 2, 3, 4 because I have sample values going from 0 to n minus 1. How the window function looks like? For rectangular window, WR of n is equal to 1 from 0 less than equal to n less than equal to n minus 1 and is 0 otherwise. So it will be 1 from 0 less than equal to n less than equal to 4 since m is equal to 5. Okay, so that is what I have written, 0 to 4. And W Hamming of n is equal to 0.54 plus 0.46 cos 2 pi n upon m minus 1. Okay, from 0 less than equal to n less than equal to m minus 1 and 0 everywhere otherwise. Again it will be 0 less than equal to n less than equal to 4 since m is equal to 5. Okay, now let us calculate. So for rectangular window the function is 1 everywhere. So no need to think much. You have to write 1 everywhere. 1, 2, 3 and 4. That is 5 times 1 directly. From 0 to 4 it is 1 always. So that I have written. But you cannot do that in this case because as you change the n, the cost is going to change. So for this we need to actually calculate the values. Okay, and the value comes as 1, 0.54, 0.08, 0.54 and here it will be 1. Okay, then we will calculate this function. Comes as 0.1344, then 0.2789, then 0.33995, then 0.2789, then 0.1344. Okay, finally we need to perform the product. With respect to Hamming window, this will be 0.1344 because it is 1 into this, and this will always be 0.1344, and it will be 0.2789, then it will be 0.33995, then it will be 0.2789, and lastly 0.1344. Okay, now let us do the product of these two values, and you are going to get the answer as 0.15, then 0.02719, then you will get 0.15, and finally you will get 0.1344. Okay, so that are the values of the table. But we need to focus on one sample which is very important. The sample as n is equal to 2. In every problem, you will find this, or in every solution, you will form this problem. Okay. If you carefully see, in h of n, we have 1 upon pi n minus 2. So if I put n is equal to 2 over here, this 2 minus 2, it goes to 0. And once you put 0 over here, this whole term will go to infinity and it will be a not defined function. Then how I am getting this 0.33995? So we'll be focusing more on this point at n is equal to 2. So at n is equal to 2, we will evaluate. Okay, at n is equal to 2, we will evaluate the h of n again. So my h of n with n, okay, by h of n, let's say 1 upon 2 pi integral minus 1.068 to 1.068 1 e raised to minus j omega 2 into e raised to j omega n d omega. Now when I put n is equal to 2, I get h of 2 which is equal to 1 upon 2 pi. Integral goes from minus 1.068 to 1.068 1 e raised to minus j 2 omega into e raised to j 2 omega into d omega, right? So that will give me 1 upon 2 pi integral minus 1.068 to 1.068, and this term will come to 1. So that will be 1 e raised to 0 d omega. Now we see that e raised to 0 is 1 and you have 1 over here. So when I integrate, I will get 1 upon 2 pi of omega from minus 1.068 to 1.068. That will be equal to 1 upon 2 pi 1.068 minus of this minus becomes plus 1.068. That value will be 0.33995. It is nothing but h of. So whenever there will be a question or wherever there will be a problem of an undefined rule in the given solution, that time you have to pick up that specific value of n and integrate, and you will get the specific value of n. So normally this value will always be the value of alpha where you will find this problem. So I can write a generalized equation for a low pass filter. So whenever you get low pass filter, your h of n should result in this. So let us say if I get a low pass filter, okay, my generalized h of n will be equal to 1 upon pi into n minus alpha into sine n minus alpha to omega c. So this will be my generalized equation after integration. This will always happen. Okay. For example, in the previous problem, omega c was 1.068, alpha was equal to 2. Okay. So my h of n was equal to 1 upon pi n minus 2 sine n minus 2 into 1.068. Okay. Just to cross verify the result, we will check the answer of our integration. So the answer of our integration was over here. The answer of this integration was 1 upon pi n minus 2, because alpha is 2 over here, sine of n minus 2 into 1.068. So in general, you will always find this as a solution of the integration, and the problem will occur at n is equal to alpha. So for n is equal to alpha, you have to find h of alpha, which is equal to integral from minus omega c to plus omega c h d of e raised to j omega into e raised to j omega n d omega. Okay, by putting n as alpha, this will go as alpha. Agreed? So this you have to perform in all low pass filter, digital FIR low pass filter. So whenever the problem comes for an low pass filter, your integration, that step 2, should end up in this form, and then when you will give the sample values at n is equal to alpha, you have to perform this integration again to give the final answer of h of alpha. Okay, so this is the final result of a low pass filter. Thank you.